Hello folks, I've got to hurry up. The sun's going down. The days here are getting shorter. Pretty soon we'll be waking up in the dark, going to bed in the dark, with hardly anything in between. So in the last video we got to recap that Yaskawa DC servo drive board. And here's the layout of the capacitors right here. I'm going to show you now how to fire up this drive and run a motor on it. It's not hard. You got to make a few cables and whatnot, but it's not hard. If I can do it, anybody can do it. So let's put the block diagram out here in front, and you'll get to see a little bit of the connections before I show you how I hook this thing up. Up here is a terminal board right here where we connect the power supplies, the chokes, and the motor thermal. I'll have these drawings up at the end of the video where you'll be able to take some screenshots so you can hook this up for yourself. Now here we have a DC voltage on the P and the N terminal. This drive monitors that voltage, and if you have less than, I don't know, 214 volts DC right here, the drive won't run. You've got to have at least a 200 volts DC and above. And if for some reason when you get it hooked up and your drive doesn't run, check that DC voltage, make sure it's up above that monitoring voltage. So that's on the P and the N terminals where that DC voltage comes in, and make sure that you have the positive voltage on P and the bus voltage ground on N. Down here is a terminal labeled little r and little t. I run 200 volts AC into that. This is a transformer, and it makes the on the secondary, it makes the AC voltages for the power supply and the base drive circuitry. Out here on the other side you have labels at the terminal board, and this is the same terminal board as the PN and N and little r and little t. You'll have what's labeled as L1 and L2. There's a choke that is connected between L1 and L2. Don't confuse this with the line voltage. That's not the line voltage. L means inductor. So L1 and L2 are where you connect the inductor. I have two chokes out here, but the diagram only shows one. When I'm testing it, I always hook up two. Now what does that choke do? You have your transistor power modules right here. You have 4 of them. When I want to run the motor, say clockwise, I will turn on this transistor power module and this transistor power module, and now current will flow, let's say from plus bus through this turned on transistor up this way through our choke back to the armature winding of our DC motor, through the DC motor armature back into this bottom transistor on this power module to bus ground. If I want to run the other way, I will turn on these two, and now Current flows through here, this one, and we go up through the armature and out the other side, through the inductor, and then down through this one, back to bus ground. So you can reverse rotation based upon which transistor pair you have turned on. What the choke does, when we're pulling current through the choke, it builds up a magnetic field. And if we have any dips in the firing waveforms to the DC motor, if we have any dips, that magnetic field will collapse and force current through the choke to smooth out the DC voltages through the motor. That's the purpose of that choke right there. Now the armature of the DC motor is connected at terminals A and B. Over here we have a motor thermal switch inside that motor, and it connects to little e and little f. Now down here, that's your power. Down here is our control. Let's talk about the tach feedback. This is a servo drive running a servo motor. When we servo a motor, we have to have feedback. And that is brought in on this blue connector. You'll see it in the pictures in the movies. And the blue connector is called a Honda connector. This particular one that we're working with has 20 male pins. And so we call it a Honda 20M. So our tach that's inside this DC motor over here, the tach connects to pin 6 and pin 12 of that blue connector. The speed reference, what makes this thing speed up and slow down, we have to tell the servo drive how fast we want to go and what direction we want to go in. That comes in on pin 7, referenced to pin 13. Pin 13 is servo ground. Now how do we tell the drive we want to go? That's this servo on bar on pin 1. The bar means that it's a low, active low input. So we need to connect pin 1 to pin 13, which is our servo ground. Okay, there's the diagram. I'll have pictures of this block diagram up at the end of the video so you can take a look at that. I'll come back in a little bit. I want to take a break. I'll come back in a little bit and we'll show you my hookups. Okay, to test our DC servo drive, the Yaskawa DC servo drive, we have to have a bus voltage. Positive bus voltage on P, and it's ground on N. Now we make the DC voltage with this circuit right here. This is a variac, a variable transformer. We plug that into the wall. Here in America, it's 120 volts AC, single phase. That's my drawing of the plug right there. It looks sideways, it looks like a mushroom. Anyways, you plug that into the wall. You increase that dial right there, that's my dial, and the little meter goes up. And I have an AC voltage, a variable AC voltage into this bridge rectifier. On the output of the bridge rectifier, I have two filter caps in series. Each filter cap is 1,000 microfarads at 450 volts. When you series capacitors, in our case, our total capacitance would be 500 microfarad. We have 1,000 microfarad divided by the two capacitors, that's 500 microfarad. But the voltage across the two series capacitors will be the addition of both these values right here. 450 volts plus 450 volts is 900 volts DC. Now we ain't putting that much into this drive. We're only putting at the most I'll put 200 volts out here. The drive, you could take it up to 300 volts DC, but I'm only going to take it up to 200. The reason I put these huge valued caps out here is we want some filtering. When we start pulling current out to the motor, we want to be able to filter any sag in the output of this bridge rectifier into the system. If we don't have enough capacitance right there, when we fire that motor up, we'll drain these capacitors and our DC bus will droop. And you'll see it in the motor. The motor will slow down. And if we had a load on that motor, which we're not, we're just testing it to make sure it rotates clockwise and counterclockwise. But if we had a load out there and we pulled too much current out there and we didn't have enough capacitance here, that motor would slow down and might even stop and stall. So we don't want that happening. We got enough capacitance right there to help us out. The reason for the large voltages is because I don't want to blow those capacitors. I bring this up to 200 volts DC right here, 300 volts DC right here. If I didn't have enough voltage top end on these capacitors right here, I might exceed the maximum rating of those capacitors, and they don't like that. They will explode. I don't want to be anywhere near that when I make the mistake of putting too much voltage across those two capacitors. So I make those capacitors very large. That's our bus voltage, our DC bus voltage to run that motor out there. Now we have to put AC into the drive to power up the control voltages and the firing channel voltages. So I do it with another variac right here, plugged into the wall, 120 volts AC, single phase, and I'll increase that voltage right there until I have 200 volts across, 200 volts AC single phase across R and T. That's power to the drive. Now let's look at the output that runs the motor. Here's our two chokes that I've got connected to inductor 1 and inductor 2. Here's the DC motor. This is the armature connections to A and B. And here's down here on the same terminal board is little e and little f. That's a motor thermal. Now every one of these Yaskawa DC servo drives that I've ever worked on, this has been jumped out because the motor in the machine, there's no thermal in the motor, so they jump this out. If you don't have this little e and little f on that terminal board jumped out, you'll get an alarm indicating that the motor's overheating, even though we're not using the thermal in that motor. You got to have that jumped out. What We fake it out with that little jumper wire right there. That simulates the motor thermal. Okay. These are the controls. Into the blue connector, the Honda 20 male connector, Honda 20 connector. We have our speed reference on pin 7. That is derived from a potentiometer right here. I use a 2K will work. 2 kilo ohm or 5 kilo ohm would work. Don't get too high. If you put 100 kilo ohm out here, you won't have enough current flow into that pin right there to be recognized by the drive. So a 2 kilo ohm, 5 kilo ohm potentiometer right here. Have one of the wings connected to plus 10 volts DC of the external benchtop power supply. The other wing of the potentiometer goes to negative 10 volts DC, and the wiper goes to pin 7. And that benchtop power supply is ground is referenced back to pin 13 SG0V on the drive. To turn this drive on, to enable the drive, you want to have a switch right here on pin 1 switched back to pin 13 SG0V. Now a note on this system right here. This drive, I've got to start out at a speed reference very close to 0 when I switch this on. I'm sure out there in the machine everything is okay, and you can have a larger speed reference on that than what I can do here in the shop. What happens in the shop is if I have this either more positive or more negative, and I switch this on, and it might be a mismatch of the inductors that I have, and that's probably the case, a mismatch of my DC motor. I'm not using a Yaskawa DC motor. And all of those mismatches and mistunings of the drive and the motor and chokes that I'm using, the drive will chug. It'll go chug, 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 chug. So I found in the shop, if I set this at 0 volts on pin 7 and then enable the drive and then bring it up to speed either in the clockwise or counterclockwise direction, it'll run. But if I start out with any kind of speed reference here, the motor chugs, and it's just because it's not tuned to the DC motor and the chokes that I'm using. Down here is the tach generator, and that is fed into pin 6, and the other side of the tach generator inside the DC motor is fed into pin 12. If you get either your armature wires backwards or your tach wires backwards, and you go to enable it, the motor will run away. So if it runs away, reverse either the armature wires on A and B or reverse the tach wires on 6 and 12. There you go. That's it. Let's go run this motor. We'll see you in a little bit. But remember, at the end of the video, I'll have some good pictures of these diagrams that you can take screenshots of. We'll see you in a little bit. Okay. I just got done installing new capacitors on this DC servo drive board. We're going to install it into the 2-axis servo drive, and we're going to run a DC motor. sure we got all of our connectors and wiring harnesses removed to the top side so we can install them. Let's get this one down here in the slot. There we go. Let's connect everybody up. That one goes there. There we go. There. There we go. Now we're ready to fire it up. Okay, we got our green power light on. There's our enable switch. Potentiometer for speed and direction. It's awesome. This variac here is making the 200 volts AC to power up the control voltage of the DC servo drive. This variac here and bridge rectifier and filter bus capacitors are making the DC voltage for the power devices that run that DC motor over there. These two chokes over here, they're required to smooth the waveforms that go to run that DC motor.